There you go. Okay, so my name is Emanuele D'Osualdo, and I'm going to be chairing the session later. This session, I mean, POPL has a very broad scope, so some sessions are more coherent than others. This one does not have a very strong theme throughout, so I'm going to go linearly over the 3 papers that belong to it. So the first paper is orthologic with axioms. So the rough idea is you may be doing a verification of a program, and you get verification conditions which are in the form of entailments, and you want to prove them, discharge them automatically, right? So you may have a formula like that, and you want to prove that it entails the formula on the right. And it may be that these formulas are in a domain that is completely undecidable or too hard to solve. And so you may, as a first attempt, try to see if, okay, what if we forget what the interpretation of the single propositions is? Does the implication hold just because of classical reasoning, propositional reasoning? And in this case, it does hold just because of classical propositional reasoning. And it's a sound inference to do because it holds for every interpretation of the propositions. So what you're doing there is you want to reason about this entailment up to the axiomatization of classical logic in the form of some laws, right? Good. So now, if we do this with classical laws, we know that this is basically SAT and it's NP-hard. So it may be still prohibitive to call this in a tool. So one strategy is, what if we only admit a subset of the laws? I mean, if we have no laws, we immediately can say false, right? It's not very useful, but it's sound, right? So what if we select a subset so that we get a faster algorithm that is still sound? One canonical or very famous subset is intuitionistic logic that gives you a p-space problem for entailment. And intuitionistic logic kind of rejects a strong notion of negation, but keeps a strong notion of implication. Orthologic is a kind of dual choice for how to weaken the laws. You keep a strong notion of classical negation, but you don't have a notion of implication that is as strong as in the classical logic. And what the paper shows is that you then have a polynomial algorithm for deciding entailment. And of course, this is weak, right? And so even in cases like this where the things almost match, but they don't really, if you look at the uninterpreted version, right, you may fail to prove validity of something that is actually valid when you interpret it. And you may try to fix it by adding some knowledge about the domain in the form of entailments that you know hold. For example, if we know that x is strictly positive, we know that the cube of x is strictly positive, although these are different propositions. So the idea is you want to admit this as an axiom, right? The problem is this is easy to do if entailment it can be internalized in the logic as implication, because you can just add an implication on the left side of the turnstile, but orthologic does not have a strong notion of implication, so you cannot do this. And so one of the contributions of the paper is to show that even if you add a finite amount of these axioms, the complexity doesn't go up. Second paper is about hyperproperties. So what are hyperproperties? So you may be more familiar with trace properties that say all traces of a system are good, right? Hyperproperties are about ensembles of traces that you want to relate with each other. An example that is very classical is non-interference, right? So imagine you want to show that in your system where there's a part of the state that is inaccessible directly by the adversary, right? And there's a part that is public and can be observed, right? You want to make sure that no matter what happens in the input-output that is accessible to the adversary cannot gain information about the secret. And if I give you a single trace, it's not clear whether that happened or not, this leak of information, right? We have an input of 0, an output of 10, the secret was 42. We don't know if 10 was actually computed from the 42 or not. So a way to go beyond this limitation is to consider two traces that start from the same public input but different secret, and you want to make sure that the public output will be the same, otherwise the intruder may detect that there was a difference in the secret and leak some of information about it. And so as a property is a property of two runs of the program at the same time that you're comparing instead of single traces. Now, this we want to specify these properties, right? So in the case of trace properties, we have a very classic logic, temporal logic LTL to predicate over these traces. There was a proposal for hyper LTL for predicating over multiple traces. So you can imagine, you have, for example, two traces, and you want to navigate them together and say something about what should happen or what shouldn't, right? And this is easy enough if you are saying things like, if I see red on the upward trace, I see red also down, right? The problem is if sometimes you don't want to look at the two traces in sync, right? But you want to say, okay, ignoring the white and gray states that may not match in number and alignment, right? If I see a red dot there, the next non-gray or white state in the bottom one is also red. Right? And this requires you to be able to navigate the traces asynchronously, and this is a problem for previous logics. And there is a new proposal for doing that within an LTL-like logic in this paper. And they show that for this logic, the problem of model checking finite state systems is still decidable. And they go beyond and add stacks to model recursive behavior of a system and prove that for a certain subclass, this is still decidable. Of course, in general, if you have two stacks, you're Turing complete, so they need a restriction. Okay, last but not least, it's a paper about abstract interpretation. So I'm going to give you the naive outsider view of abstract interpretation and then correct it, right? So the naive view is that it's just exhaustive symbolic execution, right? So you look at a program, in the concrete it would do something specific to a specific concrete state, and you can try to understand the semantics of a program symbolically by having a state that is less precise. For example, we are only recording the parity of x here, right? And we go from being odd to even, which is an over-approximation, but it's still sound, right? And the story goes as, well, on one side, you're working with concrete values or sets of values. On the other side, you're working with an abstraction of it. And abstract interpretation tells you what it formally means to be a sound abstraction, right? So there's a pair of abstraction and concretization maps that tell you, and that need to be in some relation, satisfy some axioms, and they're called Galois connections where they do. And this induces a notion of sound analysis, right, that you can do with respect to a concrete semantics. Now, there are two crucial bits that are missing from this naive view. The first bit is that abstract interpretation is actually a general framework to compare different semantics of programs, no matter whether this semantics looks like a symbolic execution or not. It doesn't need to be a lifting of a value abstraction to abstraction of behavior. It can be much more sophisticated, and these semantics may not even be computable. So it's not just about doing analysis. And the second misconception is that given a Galois connection, you can actually derive constructively the best abstract semantics from the concrete one. So the concrete one is the state of affairs, the specification of the language that's fixed. And the analysis is actually derivable from fixing an abstraction and then looking at what the interaction with the concrete is. And this removes the guesswork from designing analysis. So this paper looks at program logics, right? So lately there has been a proliferation of program logics as variations of Hoare-style logics, right? Like first-order programs, and you want to verify compositionally with assertions. Hoare logic is the most classical of them all, but there has been incorrectness, or also called a reverse Hoare logic, as a proposal for capturing more bug-finding kind of reasoning. There's also a distinction between whether your logic should be or not sensitive to termination, which gives rise to the partial versus total variations of these logics. And we have a zoo of possible logics, and maybe even more are there that have not been studied. And in this paper, it is shown that you can see these various logics and all this zoo, actually, of logics as abstract interpretations of a single concrete semantics. And this enables two things. The first is that you can compare all these logics in terms of expressiveness using the framework. And the second is you can actually derive the rules from the abstraction. So this removes the guesswork from coming up with the rules that apply for a specific logic. That's it. This is the Logic Foundation session. Come to the Turing lecture at 4:50.